Okay, great. So good afternoon. Welcome to the fourth lecture of privacy preserving natural language processing. So we're making some progress. I guess we're already in a third of the semester, roughly. There will be two public holidays actually coming up. One is next week. So next week, feel free to take the public holidays day off, including the Friday, which is the bridge day, very special day. And next one will be in June, I guess. But anyway, so we covered something already, and there's more to do, and we're taking a slow approach, so to say, but building stuff really from ground up. So just a quick check. So have you thought about? So we had like three kind of open questions last time. So have you had a chance to think about any of those? I did think actually at least about one of those, like the attacker and the counting queries. So what could be what could be the real kind of situation? So have anyone did any suggestions, anything like where this counting query could be actually bad? So what could happen? Like how the adversary could find out something just from the counting query? Any suggestions? So I mean, I'll give you mine. So I thought actually the adversary has to be strong. The adversary actually has to be able to, so if we have, for example, the counting query, so how many people have a bit, in piece of information 1 and not 0, the adversary has to be able to ask all the other people in the database. So for example, the size of the database, or so let's say you are students and I want to know who cheated in the exam, okay? And you pick one trusted curator, so somebody you trust, so it would be you. So I would ask you as the proxy, you would be the curator, I would ask you, okay, I want to know how many students cheated in the exam. And you would ask everybody basically their bit, like, I cheated in the exam, no, 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 maybe yes, I don't know. So maybe 2 of you would be cheating. So I know who is in the database. This is public information, this is fine. And I would ask you, okay, how many people cheated? And you would tell me 3, okay, cool, thanks. And now I'm gonna take each and everybody, like, just let's talk and let's go walk and talk. And then I'll push you a little bit and you would tell me, okay, I didn't cheat, I cheat, I didn't cheat, I didn't cheat. I wouldn't be able to push you maybe for some reason, or I don't want you, but just getting all this information from all the others, I would be able to infer your public information, like your private information, your bit. So I would be a strong adversary, that's fine. I don't have to do anything with any single individual. Like, I don't want to ask you anything, you have to reveal anything, but just basically from this pure query, I would be able to infer this. So this would be like one potential example from the counting query, how to get information. So I'm a strong adversary, right? So we have these strong adversaries. Okay, cool. If you have any other suggestions, yeah.
Tools that you can do, that you can ask like multiple questions. So I have built a database where there's like Alice and another person, the only two persons that have some sort of rare disease.
Okay.
Everyone else in the database doesn't have the disease, and maybe Alice uses drugs and the other person doesn't. And so as long as the other person is in the database, Alice is safe, because everyone who knows that Alice has the disease and checks the database sees that 2 persons have the disease and 1 person that uses drugs. So Alice can always claim she's not the one, but as soon as that person leaves the database, Alice is exposed as a drug user.
Right, but you need to condition on multiple queries, basically, or querying not one single attribute with a single bit, but maybe 2 attributes, like combining with and, something like that. Yeah, that's also. I think this is actually more, more kind of common situation where you kind of query a SQL database by multiple and where this and that and that and then you end up with a small sample, which could be like size 2. Okay, cool, thank you. All right, so let's move on. What were the 2 other assignments? I forgot. One was the proof of triangle inequality. So I hope you tried at least. And the other I forgot. But anyway, so if you have any questions, just drop me a line on Discord or whatever. I appreciate your feedback, by the way. So there's 73 people signed up for the course, at least last week, and 5 of them answered in the survey. So, well, I mean, it's better than nothing, so I appreciate your feedback. There were some critiques, so I'll try to fix that. And again, apologize for the last time, the slides were kind of messy. I fixed them, so the proof is now correct. I mean, proof, it wasn't proof. It's basically like the equations with the minus sign, so it's correct on Panda. All right, so let's move on today with Yeah, well, we will continue where we stopped last time. So because we're really progressing step by step towards something which we call differential privacy, but we don't know what the thing is yet. So we discussed probabilistic approach to privacy. We developed this counting query on this example, and we said like, yeah, in order to privatize this true query, so if you say like 3 students cheated, you need to do some randomness. And we talk about a distribution, which was, what was the distribution? What is the distribution we're using? Yeah. Exponential. Yeah, it wasn't exponential, it was Laplace distribution. Exponential is, so just to clarify that, exponential distribution is a thing. Exponential distribution is basically this positive thing. So this is like theta exp minus theta, which is so this is the parameter is the theta and x is the, and if you take the Laplace, which is 1 over 2b exp and minus x minus mu over b, if you take this and b would be 1, the scale would be 1, this would be 0, you get something similar, which would be like half of, so exponential is basically half of Laplace. So Laplace is basically double exponential also. So this is how it's related. But we're using Laplace distribution or Laplace mechanism as we will see later. Okay, so just one of those. Why we choose this one? Well, it was convenient to show some of those. Well, I mean, it's a probability distribution. It has some properties better than, for example, uniform distribution, because if we use uniform distribution, none of what we showed would work. So we choose this one. We might have chosen Gaussian one. Maybe we'll do it later because it has different properties that we really want. But we choose the Laplace one and show that you need to use it for privatizing queries. So again, this was the example. I just want to really refresh because we're going to be continuing with this example today as well. So we had this database, and we might have some public information, for example, the size of the data set. And the true answer to the query would be like 2 people, 2 drugs. And again, if you have this linkage attack, so somebody else reveals something, and I'm the strong analyzer, I can push people to reveal their secrets, then we will reveal privacy of an individual, and the individual didn't do anything, just it is in the database. So as we say, we have to randomly alter the result of the query. And what we want is that, yeah, the output should be close to the true value, right? Because, I mean, if I ask you how many students, so this is a thing, this is the utility. How many students cheated? And you tell me maybe the true is like, how much did you say? 3 students? 3 students cheated. And then you do like something random on top of that, and you tell me 71. So I would be like, wow, okay. Out of 73, 70 were cheating, like, that's a lot. So something is really wrong. I don't know, I had to change everything in the course. Yeah, but it was random value. So maybe the actual true is 3. And then you happen to sample something which is very far away from the mean, from the truth. And I don't want that because I want to be as close as possible. I mean, if you do that, maybe you protect more privacy, as we will see later. So I want more, I want to be closer to true value. And then we sort of took an approach saying, well, yeah, so we took the Laplace distribution, right? That's what we talk about. And we took like 2 scenarios where one person and Elise, we put Elise just arbitrarily. It could be any other person. So we took Elise, was in the data set, and then we queried, and then we kind of pretend we removed Elise from the data set and then querying. So we would get like 3 or 2 maximum distance. Okay. And then the question would be, for anything you report to me, so if you say 72, 71, I wouldn't like to kind of be able to see how much I can infer about this individual having all possible kind of information auxiliary. So to find out whether, what's the secret bit of this person, what's the private bit, this one. And we show that if we do this with the Laplace distribution on top, we would be able to kind of come up with these bounds here. So the underlying database was D for this Y and the D prime for Y. So we, this was with Elise in it and this was without Elise. And we saw that using this Laplace with the scale 1, the maximum amount of information we would get for any output, 71, 4, even minus. I mean, minus makes no sense, so maybe that's useless for me, but can happen maybe. It's bounded by some constant. This is the maximum information we can get about the person. Okay, cool. This is like sort of like information theoretical guarantees. I mean, these are actual like information theoretical guarantees, but we don't take the approach of, let's say, KL divergence or any divergence. We might take it later. So, okay, raise your hands. Divergence. KL divergence. Cross entropy. Little bit. Okay, cross entropy a little bit. So cross entropy has something to do with KL divergence, and divergence basically shows some sort of difference between two random variables. Well, we have a difference of two random variables here. So this is sort of a divergence. And we might take this perspective later on. This is not necessary right now. So we just say, okay, the likelihood of these two ratios, the likelihood or the ratio of these two likelihoods. I mean, whether it's coming from Y or whether it's coming from Y prime, respectively D or D prime. So, okay, so we say this is limited. Nice. This is where we ended up. Yeah, exactly. Yeah, that was a summary for last lecture. So for counting queries, and this is important, our query was counting. So how many people, the maximum difference of the query result is 1. Why is it so? If I remove one person from the database and ask the same, how many cheated? And so I need an example. So can you be the cheater? Sorry, just for the sake of example. So Bob, excuse me, Bob is a cheater here. And if I remove, so we were like 3, and if I remove Bob from the database, the answer would be 2. Well, no matter who was the Bob or Elise, she wasn't cheating. If I, sorry, I really need like examples. If you weren't cheating, so if I remove you from the database, well, nothing will change. So the maximum difference will be 1, okay? So this is the counting query kind of feature. And we had a scale B, and these were the upper bounds. Okay, so this is a recap of the last lecture. We're gonna extend it today. Any questions so far? So anything is kind of, you had a thought, and it's like, I don't know, like, gosh, anything. If this is the case, it's awesome, because when I started learning something about differential privacy years back, I was like, why did they take like two different databases? And so if this works for you, that's awesome. So today, well, we need to talk about some concepts, some formalisms, which we know already somehow intuitively, but let's put them into like more formal kind of treatment. So the one is a very important concept in differential privacy, which is called the notion of neighboring data sets. Okay, so because what we saw before, that our bounds were kind of symmetric, right? So if we had the database here in the nominator, and the denominator would have one item less, we have the same bound as we just flip these two. So these are kind of not the same, of course, but symmetric in a way. And on the left-hand side, there is one entry less in the denominator and one entry more in the denominator, and this is the other way around on the right-hand side. So this means that this bound holds for any two data sets that differ in the presence of one entry. So either you remove one entry or add one. These are equivalent, right? I mean, here, if you have a data set with Elise and remove one, you have a data set without Elise. If you have a data set without Elise and add one, you have a data set with Elise. And the difference of one person, one row in the database. So remember, our database is still basically a table with rows. So if you remove one row, these two databases are going to be neighboring data sets. Okay, so this is the concept from differential privacy world, and they basically differ in one row, being it added or removed. Now, there are two kind of flavors of these neighboring data sets in differential privacy. So one is this one, where you remove one item, and there could be another one where you replace one row with someone else. And they have names. Also, these two flavors, which I actually forgot right now. Bounded or, oh, sorry, unbounded or bounded. I will look it up. And typically one of them is a little bit stronger than the other. So this adding and removing have some better guarantees than just replacing in some circumstances. And to be honest, it doesn't really play that much role. In some cases, it's important if you have two neighboring data sets by one extra row and not. And in some other cases, the bounds are similar or up to some factor. And I'll try to pay attention to when we have an algorithm for preserving privacy, that we make sure that we are neighboring data sets that differ by one row. If there's something else, I'll make sure that we know what these are. But this is an important concept, like neighboring data sets. So neighboring data sets, an example, pretty simple. So the first database 1, including Elise, Bob, and Charlie. Database 2, I excluded Elise, and the choice of Elise was arbitrary. So these two are typical neighboring data sets. If I remove 2 persons, it doesn't code as neighboring data set. Okay, so this is why we talk in we had these 2 scenarios. What if I remove Elise from the data set? What happens then? So this is based on the notion of neighboring data sets. And why? Because if you remove 1 person, which is arbitrary, then maybe her information is not that her information will be somehow protected by this randomness. Okay, so any questions? Neighboring data sets is a very important concept, but it's actually very simple. Sometimes it's kind of hard to say what is neighboring because we are talking about texts and we're talking about images, and we had this notion, if you remember, that the rows have to be independent. So there can't be any information in one row about somebody else from the other row, okay? Which maybe in practice holds or not, depending on the use case, okay? But we need neighboring data sets, and we need this kind of assumption. The most important assumption in one row, this is only pertaining to this one person, not to the others. Okay. So the databases 1 and 2 from the previous slides were neighboring, yes, sure, as they differ in presence or absence of a single row. Again, this is the definition. And we denote them as D and D prime. But again, this is an arbitrary choice. We could call them D prime and D, or X, Y, or X, X prime, or whatever. So if you look into the literature, you see like all the different namings, including Greek letters or whatever. So D and D prime is one of these options we're going to be using, at least today. So, which means then we have this kind of bounds that we say for the ratio of any reported output, 371, for any 2 neighboring data sets is bounded by this X of 1, which is 2.7. Well, we actually can just say, well, let's use just one equality, because if these 2 are neighboring, then we can create one of these 2 out of that, right? I mean, for any choice of neighboring data sets, this kind of bound holds. Does it make sense? It's just, I mean, one formula less, because we're encoding basically everything into saying, well, these 2 differ in one row. And it could be the upper one has like 1 extra or 1 less, which gives you one or the other from these 2 sides, okay? So this is nice. I mean, we're simplifying stuff. So we're saying, well, for any 2 neighboring data sets, in our example of the counting query, we kind of have this nice bound of something, E21. Okay, any questions? Okay, cool. All right. So we can restate our bound with neighboring data sets again. So again, neighboring data sets presence or absence of a single individual. And as we saw, our bound holds for any neighboring data set. And again, okay, I mean, we did it last time, basically, why this holds. I mean, these were these equations where I screwed up the minus sign and fixed again, but you can prove it again. I mean, really convince yourself. If you have 2 neighboring data sets and you do this counting query with the Laplace, that it will be bounded by this E to 1. Okay, make sure that you can really understand this, back and forth. I'm not saying it will be in the exam. It might be in the exam. I don't know, but it's somehow important that you. I mean, this is very simple, like multiplying, working with the exponential. Excuse me, with the Laplace PDF. So what does it mean now? So the absence of presence of any single individual will influence the result of the counting query. That's true, right? I mean, yeah. Of course, if I have one more person with the disease or with drug use, the result will be a little bit different. Even after, sampling randomly from the distribution centered about the truth. So one truth would be 2, 3, and without Bob, it would be 2. So the random values will be kind of parameterized by this, by the center, okay? So it will influence the result. Depending on how much noise, maybe the influence will be smaller or larger, but I won't, I as somebody who is interested in getting some information about it, I want to keep this influence small. So I want this utility be as small as possible. I don't want you to say 73 if the true was 3. I want you to say, I don't know, something. I want you to say actually 3, but you can't. So the chances you will report 3, but I don't know because it was random and I cannot like undo your randomness. So I'm gonna tend like, yeah, the utility. Okay, so here's one thing that could be interesting to think about. Whatever we do with this, if we use this Laplace and for counting queries, I mean, of course, there will be some error, inevitably. Like if you do anything random, you're adding some random noise, and of course, my result or what I hear from you will be with an error. So compute. So it should be possible. What is the probability that I am one of more than one of? So what is the probability that how to write it actually? So you know what I mean? I mean, if the truth, so okay, let's see. If the true is 3, what is the probability of the report that it's larger than 4 or smaller than 2? Right? I mean, I want to know like how bad the error is. Can you do that? I mean, I think you should be able to do that because this is if we're using the Laplace distribution underneath, and if you know the PDF of the Laplace distribution, so what can you do with Laplace distribution if you have the Laplace distribution? So here's a hint. So here we have, how's it called? Say again? Expectation. This expectation, exactly. This is the expectation or mean, or I call it mean or expectation, or E of, this would be Y, for example. Yes, this is the same value. So expectation. And the question I'm asking is, what is the probability that I am more than 1 from expectation? How can you compute this kind of probability? What technique you need to use for computing probability if you have PDF, probability distribution function? You have to integrate, exactly. You have to, and you can make it easier actually here to see like, well, it's actually symmetrical, so I just do it. I do one integration and then just multiply by 2. That's one trick. Or you can just integrate 2 integrals, which will be the same. Well, I mean, the result will be the same. And sum them up. Okay, so this sounds like a great homework, I guess, for you to kind of explore. No, I mean, I'm serious. I mean, we can do it in the exercise if you want, but I think you should kind of a little bit struggle with that, because then once you start doing this, you realize, oh yeah, either you actually realize, you actually understand what we're doing with the Laplace distribution and the Laplace mechanism. This is great, or not yet. And while doing this, you wonder, oh, sure. I mean, yeah. Okay, yeah, makes sense. So the probability of being 1, and then I'll ask you, well, what is the probability of being 2, more than 2, or standard deviation? Like how far, like what is the standard deviation left, right, and things like that. And this is like great exercise to reason about. Basically, what you're interested in is like tail bounds. And I think tail bounds, or well, knowing what's on the tails of a distribution, I think it's a topic in statistics or mathematics. I mean, statistics absolutely is like tail bounds. What is the probability that you are not in the middle, but somewhere far off? And for the exponential distribution, it's really easy to do with integration, because the integral of, you will see. I mean, it's fairly easy. It could be like 5 lines of not code, of math. Yeah. Okay. So this is the utility. So this is what I want to do as a good guy or a bad guy, because there's no distinction between a good guy or a bad guy. Okay. The thing is, and if I'm a really, really bad guy and I have all the compute power or everything, the likelihood to find out the extra person's private bit, for example, drug use, is upper bounded. So upper bounded by this thing. So, and the person who is in my database wants to keep this bound as small as possible, right? So of course, the less I can infer about presence or absence of any person, the more privacy I'm getting. So, any questions? All right. And now let's talk about exactly this, like how to control the strength of privacy. Like, what does it mean? I mean, we saw like E to 1. Is it good, or is it enough, or could be better? Or I mean, this says something about the strength of the privacy, of course. But can we control it, and what does it tell? So let's have a look at this. So what if this is not strong enough? So again, here what we did with our counting queries. So we reported the y by telling the true, which is 3 in this example, and sampled from Laplace distribution centered around 0 with the scale 1. So the scale 1 was arbitrary here. Okay, so we choose b as fixed scale here. Okay, and this gave us the for neighboring data sets, it gave us this bound, which is e to 1, which is 2 point, the Euler's number. The question is like, what could be the minimum of this? So what could be the minimal bound we can get, and what could be the maximum bound we can get? So let's start with the minimum. So what could be the minimum of this? So the probability, I'm seeing something with LEs, and over the probability, I'm seeing something without LEs in the database. What could be the minimum of this ratio? Any suggestions? What could be the minimum of this ratio? I mean, we saw an example. I mean, it could be 2.7, could be smaller. Yeah. 1 what? 1 by E, or 1 over E, or? So this is one candidate, 1 over E, which is 1 over 2.7, which is 0.33. Okay. Any other suggestions? So this is candidate A. What could that be? Could we do any stronger? So I would say, like, let's forget this. Like, this is a number, okay? So what could be the minimum number we can have here on the right-hand side? So we have a ratio of 2 probabilities. 0. Okay. So this is candidate B. Would it be 0? For any neighboring data set, what could be 0? It would mean like the probability will be always 0 for the top. I mean, how can you get 0 from this? So this would mean like the denominator must be 0 for any y. But do you know any probability distribution which gives you probability of 0 for anything? Not really. So yeah, so it can't be 0. I mean, the probability must, for some output of the probability distribution, it has to be something bigger than 0. So that won't work, I'm sorry. So okay, so it won't be 0. This is still holding a candidate. So anything else? What could be the minimum? Yes. Something close to 0. Okay. So C. Something close to 0. Okay, interesting. So shall we? Okay, so this is stronger than this up here. Okay, so shall we vote? So who is for A? 1 at least, I guess. Okay, who is for C? 1 at least. Come on, I mean, this is your suggestion. Okay, cool. No, so let's think about it. Okay, so we have two neighboring data sets. So what if we say everything is completely random and we don't take any information whatsoever. Everything is random. So let's say here the probability distribution will be, well, what could be the simplest probability distribution? So the simplest probability distribution could be, what is the simplest probability distribution you can think of? If somebody tells you something about probability, what's your first kind of idea? I would say throwing a coin. Probability, yes, sure, tail or heads. Okay, yeah. So this is Bernoulli, and if it's fair, then its probability of heads is 50%, 0.5 and 1/2 for the other. Okay, so what if this were Bernoulli? So heads with 0.5 and tails with 0.5. And what if this was also completely random, heads and tails? Then you get 1. Okay, it's interesting. And now I actually forgot the true answer. This is interesting. So I think it actually should be bounded by 1. I guess the true answer is 1 because you can't do any more random. This is like the most random you can get because everything is random. It doesn't depend on anything in the data set. You just throw a coin and throw a coin. And you don't care, what's in the data set or whatever. It can't be any more random. And if it can't be any more random, the ratio will be 1 for any 2 neighboring data sets. Does it make sense? Okay. So I guess this is 1. I think the argument it's actually because of that. Like if you do it truly random, well, the ratio, okay, well, if you say like, is it more likely from this distribution or this distribution? Well, if the distributions are the same because they're completely random, regardless of whatever is underlying, you have 1. You have the same distributions and the ratio will be always 1, independent of which side you look at this. Okay, so that's 1. But thanks for your suggestions. Here, what would be the maximum? What could be the maximum sort of loss? What can I learn about persons? What could be the maximum bound? So if this is private, there is some number, there is some bound. What if this is non-private? So this is unbounded, right? So what does it mean if it's unbounded? There will be a very beautiful number, which is not a number, which is something like infinity. Why? Well, if you do something which is not random and always depends on the data set and there's 0 randomness, then of course you will hit some, there's unbounded. So if there is no randomness, for example, you always report 1 value and you know this, you will always report 1 value, then you lose your complete information. Okay? If this is not yet clear to you, I would suggest to think about it and try things like on your own, like depict something and say like, well, what if I do the Laplace here and to just kind of get an understanding what this bound could be. Why this is 1 or the other? Well, why this is and okay, so let me be really sure. Is it really 1? And I have to really double check because now you really confused me with these, you really confused me. But I guess e to 0, yes, this will be 1. Exactly, yeah. For this argument I just said before. Okay, maybe there's a formal proof somewhere. Okay, so and why we discuss it right away. So, okay, so this is nice. So we have some sort of strength of privacy here. If this ratio is 1, then all options are samely possible for any underlying data set, and it could be, wow, it can't be equal to infinity. I'm sorry, it should be less than infinity because this should be a real number. I mean, if it's infinity, then something is broken and it's not private. So let's put it like that, but you cannot really get like infinite as a number. But it could be 1 if this is completely random, so no information. And of course, if this is completely, you see like the strength of privacy has something to do with utility, because if it's completely random, then I ask you how many people cheated, and you say some completely random number, which has nothing to do with the underlying data set, then yeah, you have everybody has perfect privacy. Everybody has perfect privacy. Because even if I took everybody except Bob, and they tell me their numbers, I cannot tell anything like whether or not. I don't know, because everything was just completely random. So You know, here's the trade-off: randomness, or privacy and utility. Okay. So we want to do something about, in our case, of the counting query. And one idea, because we choose the parameter b, like just one. We say like it's convenient. Let's pick one. So how about we play with the scale parameter b? And here I'm again, well, not again. I didn't show this this example last time for this Laplace distribution slide. There was this kind of to do, and I tried to draw it very badly. So I made it up here again, and to show different Laplace distributions, so to see that you really see what is what the scale and location is doing. But let's start with the scale. So here, this blue one, can you see the colors? Is it somehow? Yeah, okay. So the blue one here in the middle, it's the zero center Laplace with scale 1. Okay, so this is this distribution in the middle. Now what happens if I increase the scale of the Laplace? So what's going to happen? I mean, the scale has something to do with the width of the distribution, and I'm getting this. Is it orange? I guess so. Or some of those. Well, what is this color? Is it green or something? Orange. Well, a weird color. So this weird color. So basically, what I'm getting here is that the tails are getting more spread. The distribution is more spread and is getting heavier on the tails. So basically, I'm getting more uncertainty, right? Yeah, sure, makes sense, because the scale is really corresponds to variance and standard deviation of the distribution. Okay, so on the other hand, if I make the scale smaller, I'm getting more like sort of concentrated distribution, and the tails are, well, not less heavier, but are more concentrating towards the mean. Okay, so I'm getting decay much faster. Okay, so this is basically the scale of the scale of the location. So okay, and here I just for reference I put a Laplace shifted by -2. So the mean doesn't have to be 0, could be something else, but you see basically all the properties hold. You can shift it and basically scale it to be more broader or tighter. So what can we do with the scale for stronger privacy? So if we want stronger privacy, so here we had this kind of thing. We do Laplace with scale 1, and it was bounded by some things. So what can we do to get stronger privacy? What if we want this number to be small, the smaller, I mean, less information? So intuitively, think about it. Bigger scale gives you more sort of randomness. Less scale gives you less randomness. So what do we need to do to get stronger privacy? Increase what? You need to increase the scale. So you would say this would give me better privacy than this. So this is better. The 2 is better. Scale is increasing the scale. Any other suggestions? Everybody agrees with that? I agree too. Makes sense. Intuitively, it makes sense. Thanks. So why is it so? Here's the intuition, like just looking at these distributions. So we had this example of counting 50 and 51, and this was without LEs, and this was with LEs, and we put a Laplace distribution around this. So, and then we are saying, like, for any value which we report, the ratio of this to this is bounded and vice versa. Okay, so this was the scale 1. Now if I put scale 4, we're getting actually much more spread here. And as you might see, oh, wow. Okay, for the same value, like 53, the ratio of this as compared to this is getting smaller. So the distributions are getting close to each other, which means we're learning less and less from these 2 different possible data sets. Okay, so this is the intuition. If you add more noise and protect privacy, but here's visually like what is Laplace would be doing. What would be the opposite, by the way? What could be like the worst kind of, well, not the worst scenario, but just imagine now not for stronger privacy, but for super weaker privacy. It could be that we would have around 50, and here would be 51. Around 50, we would do like super peak distribution. And around 51, we would another super peak distribution, right? So then the ratio, I mean, of course, this doesn't end here to 0. It goes to infinity to 0. But the ratio will be much bigger if we see it from one or the other. Okay, so this kind of controls our how similar these distributions are. And this is what we want. We want the distributions to be more similar, or actually almost similar, regardless of whether one person is in the data set or not. Okay, so this was like kind of intuition. Then here's again depicting the actual sort of privacy loss, the likelihood that it comes from one or the other. So this is something we had in the last lecture as well, and we showed this one example. This was for scale 1, and this was the upper bound. So everything is upper bounded by 2.7. So this was our case. But now, if we use the scale 4 for the same queries, so 50 and 51, now we're seeing it's getting somewhere much smaller. So we're actually, making the ratio much smaller, and the distribution will look more the same for any value, coming out of it. Okay, so this is the intuition, which makes sense. You came up with this, but now we're showing this, and then maybe we can try to formalize it. Okay. So let's do the example again we had last time, basically. So we had the true value of query was 51 and the other was 50. So remember one data set with Elise and the drug taking and one with odor. And you look at the ratio of these distributions. So last time we kind of ignored the B, the scale, but now we have to plug it in so this is a PDF of Laplace. Okay, so if you don't know PDF of Laplace yet by heart, learn it, because it will be very convenient to know it. So we're just doing the mathematics. I'm just gonna go through right now so that we kind of understand everything. So I try to put it in detail and double check it's correct. So if you spot any mistake, I apologize for that. I try to be correct. It looks that it's actually working. So all right, so we are just expressing this as a probability distribution. Remember, if you want to be really hardcore probability theorist, this would break because you can't have like any value for continuous probability distribution because of the underlying kind of support. No, whatever. So we said like, okay, we replace this probability function with a probability density function and it will work. So let's take it for granted. We have PDF here. So we're gonna cancel those. Awesome. And then we're gonna take this plug here, and it's gonna flip the value, so it's gonna be plus. And we're gonna take 1 over b up front. Okay, so we have 1 over b, and then the rest is, I think there should be a parenthesis here to make it really clear. Okay, so parenthesis is here, 1 over b. And then here, oh, what do we use here? I mean, we're putting inequality here. So what did we use here for doing this? Second? More or less? Yeah.
Absolute.
Yeah, so the inequality, like the triangle inequality for absolute values. This is what you prove. So this is what we had last time as well, and we just plug it in here again. So this is the only trick kind of showing that this inequality holds. All right, and a little bit of mathematics. Okay, so I'm gonna kill those. Okay, I'm gonna flip this. This will be plus. No, this will gonna cancel. This will be plus. And okay, cool. Minus, plus, 1, absolute. Okay. Oh, okay. Ah, cool. So now the bound is somehow proportional to the reciprocal of one of b. So 1 over b. Ah, interesting. Okay, cool. Will it hold for the other way around? So if this were, flipped, basically, I believe so, but just for getting your skills done, just prove it. Will be the very same example, but you shouldn't make any errors, I guess, or just try. Okay, so once we will do this, we'll find that now with the scale in it, the b, we're getting bound proportional to b somehow. Okay. And it makes sense, of course. We saw it, like if we make a bound small, bigger bounds will make me smaller bound. Sorry, excuse me. Bigger scale will make the bound go down, and this is it. And this is how exactly it's working, and we can prove it. Okay. Any questions? Awesome. check here that I'm recording. I guess I'm recording. Well, if not, then never mind. So this is nice. So what we have discovered so far, we're really doing like by example, and trying to build up from scratch. It's kind of really tangible. So you can really try everything and even code it up in Python, and you see it will really work. So we are not really abstract. We're very concrete because there's some 50 and 51, which is just, well, these 50 and 51 were arbitrary. So the same proof will hold for any true answer which differ by 1. Okay? And why they will, the thing is, in counting query, they will differ by maximum 1. So this is great. For counting query, this will hold all the time because the maximum difference in the result will be 1. Either you're in or you're not. Okay, so for counting query, the database curator, the trusted curator, so this is you who knows everything about them, I don't. You protect privacy of all these individuals here by reporting the true value plus adding something with Laplace with scale b. How much privacy you want to protect of everybody in here is determined by this parameter, this scale, basically, right? This scale will help you to make stronger or less stronger. And also my utility bigger and smaller. So if you do this exercise, then this one, yeah, maybe think about the scale. Don't do just like the scale is 1. Just plug in the scale in there because the scale actually influences, how far you off or not. So generally should be like the general PDF of Laplace to do this. It will play out nicely, I can guarantee you. So this is great. So for any neighboring data sets, Bob, Elise, whoever, the privacy loss is bounded by this value. And we know the bound is, so now we know the minimum would be, well, if B was, okay, so this is interesting also, in another take, like why this is at minimum 0, or not 0, sorry, greater, it has to be greater than 1. I mean, the only chance where this would be 1 would be 1 over B, and B should have to be infinity, because x of 0 is 1. And if B is infinity, what is B infinity? It means the Laplace is not like that. It's basically uniform. Oh, and we're there. I mean, uniform gives you no information what the mean is. It's just everything is possible. I think the Laplace distribution actually doesn't support B to be infinity, so it should be some actual number. But the more it grows, the more uniform the distribution would be. Okay. Cool. So we discovered basically a little bit of, well, we discovered basically differential privacy by this counting per example. So we should maybe formalize it now a little bit more. But do you have any questions so far? Is everything a little bit clear or less? So the working examples should kind of help you to really digest it more and really try to code it up, and maybe one or the other proofs to familiarize yourself with these working examples. Because now we're going to formalize it in a way, and typically in some books or tutorials, they start with the definition and then work out the examples, and I find kind of it's possible, but the definitions are kind of like too abstract maybe to begin with. So we took a different approach. So let's try to generalize now. Okay, so we have this bound. So the ratio of observing of any value coming from one or the other set was in our counting query. So this was e to 1 over b. So we saw that 1 over b controls the strength of privacy. Okay, so let's generalize this notion, and we can call it the privacy budget. Okay, and this is epsilon. If you're LaTeX people, then this is var epsilon, but also epsilon works well as well. Epsilon, it gives you a little bit different shape. Okay, so if you're really into typography, then these are two different things. Anyway, so I'm using var epsilon. So this is the privacy budget. So this will be our epsilon, var epsilon. And if epsilon is 0, then how much is x of 0 is? What is x of 0? So how is exponential function looking like? something like that. So what is x of 0? 1. 1. Okay, 1. Very important fact. Okay, so this is something you must know. Okay, x of 0 is 1. How much is logarithm of 1? Yeah, exactly, because why? I mean, by the definition of logarithm and exponentiation, okay? Okay, cool. So if epsilon is 0, this gives us what? It gives us complete privacy, because this will become 1. And as we saw, there is no information whatsoever we're getting from that. So everything would be completely random. It's complete privacy. And the other bound would be infinity, which is no privacy whatsoever. So it's basically, there's nothing. Like there will be a way where for some value, you will kind of reveal everything, or there is no bound for this. And again, for our counting example, we have epsilon of 1 over b. Okay, so this is the naming convention. It's called privacy budget. So you might be asking, why is it called budget? I mean, privacy makes sense because it controls the strength of privacy. Why is it called budget? As we will see later, you can spend it wisely, and you can divide it and spend it in different ways very wisely, and it will somehow, you can have a budget not just for one query, but maybe multiple queries, and you can spend them, by dividing for each query, and then if you spend your budget, you're done. So that's why it's called budget, okay? But we don't do this today, but this is the naming convention. So privacy budget is epsilon. And of course, the smaller, the better for privacy, but then we're losing utility. So this is one of the hyperparameters. Now, if you think about it, well, okay, I'll come to that later again, to the epsilon, okay? So remind me of that maybe if I forget it. Okay, so let's formalize pure differential privacy. So it's another term. So we're gonna go pure differential privacy today. And we're just gonna rewrite this, this ratio bounded by this, just simply multiplying by the denominator to get this, this formula. Okay, so this is the same thing, just rewritten like to be on one line. And now we're also gonna generalize our random variables y and y prime by saying they are some random variables parameterized by the data set. And we would call them randomized algorithms or randomized mechanisms. Okay, so why they are randomized mechanisms or randomized algorithms? Yeah, well, there is some random variable or some randomness in there, and you take the true database, get the query, and then do something with the query random on top of that. So it's like an algorithm. In our case, it was just the Laplace mechanism, or Laplace algorithm was, yeah, just take the true value and sample from Laplace based on this true value. Okay, so this is the naming convention. It's called mechanism or algorithm, but it's just a random variable because it outputs a thing with some probability distribution, and it's parameterized by the data set. So we're gonna use this calligraphic M of database D or M of database D prime. So this is just naming convention. So when you see it somewhere, you will understand this is the same thing as just using this simple random variable names. Okay? Any questions? Does it make sense? Yeah, it's just making it more complicated and more abstract in a way, but we're getting somewhere. It's just naming things differently for some reason. So we're gonna rewrite this using this randomized mechanism or randomized algorithm into this equation. Okay, so this is still the same thing. So everybody should now still understand what this means. Okay, so we have two databases, and there's some randomness on top of one and the other, and the D and D prime are okay. Okay, sanity check. So what is D and D prime? How do we call them? Neighboring data sets. Exactly, neighboring data sets. Very important concept. Neighboring data sets. Okay. So far so good. Well, let's move on. So what we had in the previous slide. So it was this one-liner. And now, okay, so this algorithm or this random variable is producing something. We don't know what that is. And so far we had Laplace random distribution, which outputs real values, I guess. Yes, real values. So, but we want to make this definition. So we're going to turn this into an actual definition, but we want to work this definition for any random variable. So it could be categorical. It could be like coin flipping. So we have two values only. which are not sorted. So, I mean, we tell them like 0 and 1, but it could be throwing a die, for example, or something like that. So we want categorical distributions. We want some discrete distributions which are finite, so something between maybe 1 and 100. Why not? Uniform distribution for integers between 1 and 100. That's a distribution. So you want to do this as well. Then we might want to do it for some infinite output. Why not? Like how many, I don't know, how many stars are in the in the universe? It could be infinite. No, I think it's still fine. Never mind. I mean, mathematically, you have sets which are countably infinite, and then you have these very weird uncountable sets like real numbers. And we want this to work for anything, basically. Like it should output anything and should still give you some probability. So people typically say that the domain, okay, so what does it mean? Sorry, codomain. So what is a codomain? We have a function which goes from domain to codomain. That's just the terminology. And the codomain of this mechanism is some arbitrary set, could be some very weird number. And typically, if you have something which is an arbitrary universe or something, you use this calligraphic kind of weird letters. So, and we want that our privacy guarantees hold for any possible output y, which is any subset of the codomain. So, okay, that's kind of heavy formalization to kind of counter for any possible outcome of this randomized mechanism. Well, if you think about it, and then you just rewrite this kind of very nice, equals to y to element of set, because as we had in the first exercise, remember, everything is mathematics. Like down to earth, there is a set theory. And these are just great, and in probability theory as well. So everything is kind of could be expressed as set. Well, what could be an example here is that if our random variable is, for example, here it could be Laplace. So you might be interested actually in, well, what is the probability that I'm in some interval from plus something until something? Or what is the probability I'm in this interval, or in this interval, and in this interval? And for all these things, that has to hold. So here again, well, we saw like, well, in this number, we want the ratio to be bounded. But it doesn't have to be just a single number. It could be, well, for anything between 51 and 52, this one, and this is, excuse me, 51, 52. So this is the other distribution, like the underlying underneath. I want these two events be bounded as well. The ratio of observing something in an interval should be also bounded. So for any event coming out of here, we need to protect basically, well, we need to bound the ratio of observing one or the other. So this is why we're kind of using this very, very formal way of, well, a set, a membership of a set, and this set could be anything. Yeah, well, at the end of the day, what we actually care about is, yeah, okay, we use a probability density function of some known distribution. But I believe this comes from, I mean, they don't say what a z could be because it could be anything. So you might want to look up this definition in this book from Cynthia Dwork and Aaron Roth, which is so-called the Bible of differential privacy, so to say. But it could be unspecific in some cases, which is this one. Anyway, so but still, we are still, just the same kind of bound here, but expressed differently. Any questions? So if you see this definition for the first time, then trying to construct what this could mean might be also possible, but I took the approach of starting from something concrete to getting something very abstract. We started with the one example to something which we think could hold for more examples, and we are now starting adding more examples to this definition. Okay, so this is my approach here. So now, finally, lecture 4. So we have this pure differential privacy, and we call this epsilon 0. Epsilon, we know. So epsilon again, what was epsilon? The privacy budget. Okay, so epsilon, why 0? Because there could be another letter which will play a role later on. But now there is a 0, so we call this epsilon 0 differential privacy, or the pure differential privacy. So a randomized algorithm, this is the definition, by the way. So this is if you start this book on which is like 240 pages, on page 7, there is a definition. And it's like, and now, and let's like work it through, okay? So the definition is that a randomized mechanism is differential private if any two neighboring data sets, D and D prime, and any output Y, we have this guarantee. So this is the definition of pure differential privacy. But now we know exactly what this means because we have at least one example we work through. So we know exactly what we're bounding. We know exactly what neighboring data sets mean. We know exactly how this works for the counting query, and we know exactly how to make it stronger or weaker in this counting query example. Okay? I hope so. That was my intention. Like when we arrive at this definition, we have pretty good concrete grasp of what this could mean. This could mean many things. This doesn't have to be like just counting query in the database. Could be much more complicated, of course, because what is this? Could be anything. What is MD? Could be anything, randomness, you know. But we know what it means, at least in counting, because this is like a simple example. Okay? Any questions? This is great. So, yeah, time. So let's move on. And as I said, like we have one example of epsilon zero DP mechanism, but let's try more because our query was kind of limited. But like counting people in the database, it's kind of boring, right? I mean, and you may be asking like, what does it have to do with natural language processing? You know, well, we're far away from that, but we need to get these kind of foundations, you know, solid, rock solid, I would say. But as we saw, I mean, we have now the definition of pure differential privacy, and we have our example of counting query with this Laplace distribution. And what we basically constructed from scratch by trial and error was this Laplace mechanism. So this is one example. Laplace mechanism for counting query is epsilon zero differential private. Okay, so this is one example of the algorithm, and it is a proof. So the counting query report number of persons with a certain attribute. Okay, so you know, taking drugs or cheating in exams, or I know you're not gonna cheat. It's okay. I know. I trust you. But we can try. No, actually, there's another experiment we're gonna do about cheating exams, and it's differential private. And it's in this one, I'm gonna ask each and everybody of you whether you have cheated or not, and you have to tell me. Okay, but we're gonna do it in a private way. So, but I don't want to reveal that. So for now, you are the trusted curator, so you ask everybody whether they cheated or not. Okay, so we can try it, you know, at the end of the lectures. Could be a nice example. Anyway, so this is counting query, and we're gonna use this. This is repeating again, but just for the sake of clarity. So we're gonna draw a random number from Laplace distribution now with the scale 1 over epsilon, and we're gonna add it to the true value and report back. Okay, so you're gonna first ask, okay, how many cheated? 3. You say, okay, 3. Then you're gonna say, okay, what is my epsilon? Oh, this is a good question. What should the epsilon be? How to choose the epsilon? Oh, okay. So how to choose the epsilon? It's not $1 million question. It's a setup of the thing. Like it's an agreement where if you're gonna be in the database, you have to tell, or you have to have an agreement like, oh, okay, I'm gonna sacrifice my privacy for epsilon of 1 or 0.5 or 10. I don't know. Nobody knows. So this is sort of like a hyperparameter of the whole thing. And there's studies now, like for which epsilons are actually acceptable for people to maybe, you know, like donate data, and it really differs from scenario to scenario. So this is a hyperparameter that we kind of take for granted, but in reality, you have to be very clear about the epsilon. And remember, okay, one thing, epsilon. Maybe you should spend a lecture on that. So if epsilon is 1, fine, why not? Could be. Epsilon should be small, right? I mean, we want this epsilon to be small. Something between 0 and 1, maybe it's okay. Maybe, who knows? But maybe it's okay. Well, if this is 2, well, yeah, it's maybe still okay. Depends. But it doesn't grow linearly. That's the point. You know, if you have epsilon of 10, it's not 10 times worse than of 1. It's exponentially worse. Okay, so remember, and e to x goes around 0. It goes almost linearly. So if you have 0 and 1, this is almost like a line, right? So this is fine Between 0 and 1, it's kind of like, could be linear sort of. But then it goes just crazy. So this is maybe here you can kind of have intuition like, yeah, maybe 5, maybe 0.5, 0.6. But if you cross like 10, yeah, well, what does it mean? What the probabilities of seeing one or the other is e to 10. It's a lot. It's maybe there's no privacy at all with epsilon 10, like very little guarantees. If you have epsilon 15, like it's just the ratio is just exploding. Okay. Anyway, so where were we? We are here. So you would report this. You would have to agree with epsilon is fine. Let's say I would say 0.1 is super strong privacy. Like I would say this, like based on some other papers and people are doing things. So you would then ask, draw from Laplace with 1 over 0.1 and report the value back. Awesome. So this is our Laplace mechanism. And can you prove that this is epsilon 0 differential private? Well, we did this already. We basically constructed the whole thing from the neighboring data sets and playing around with the PDFs, but prove it. Prove it now that for counting query, using this thing gives us this, that this will work, that this is differential private. And then there's this bound on this, okay? I really strongly suggest to, so this is homework number 2. And you have everything what you need for doing this in the slides, but you have to like, kind of, do it in reverse way. And that this actually holds differential privacy, okay? Do I, is it okay? I mean, am I asking too much or too little? You will find the answer on the internet, maybe. I'm almost sure. I mean, you will, for this, you will find the answer, but it kind of gives you the, a little bit of understanding, like this is not about coding, this is a little bit theoretical, but not that much. I mean, that's not that brutal. The only thing you need to know is like how the Laplace distribution is looking like. And, once you spend half an hour with 1 over 2b x to 1, you will understand, you will remember. So, okay, Laplace mechanism for counting queries is fine. What if we want more? Like, I don't care about like how many people, I want more, I want to ask more. So let's try some general numeric queries. So we had a counting query. It reports a number of persons with certain attributes. So typically, the codomain would be some subset of natural numbers. Yeah. So what I want maybe some real valued query. So which reports any value computed over certain attributes. So like any value. Okay. So I want something like where I just report some value. So what could that be? Any idea? So I have a database of students or patients. So what could be my real valued query? What I'm interested in? And examples. What could be this? So for example, an average age. Okay. Anything else? I'd be interested.
Average number of international students.
Every number of international students. Yeah. So the average, like basically some statistics. So the mean query is something which people are interested in. So basically, I might be interested in like, well, okay, what fraction of students are cheating, which is somehow related to the counting query, but it's a difference. So you need to know the size of the database. Maybe it's public information, and then from those you just do like the division. So, but maybe I want something more than just the average, because average is basically counting. So maybe something else. I made up an example here. So there's a bank, and the bank has accounts, and each account holder has a debt. So they have like mortgage or something, like they're owing bank the money. And there's Elise, Bob. I mean, Elise maybe just bought a house, and she's really in debt, or she's studying prestigious US university, so she had to borrow money from the bank. And maybe there's other people like Sander is really he doesn't spend anything, and he just he has no debts, so it's possible. Okay, so this is a made up example, but just to show like yeah, and my query would be like, what is the total debt of the bank? Because maybe I'm an agency like European Central Bank, and I want to know like, okay, so tell me how's your debts on your bank, because if you bankrupt, so well, I have to take care of that. because the maximum debt the bank offers. Okay, here's an, maybe I should have done a better example. Because, okay, now just, maybe I'll fix it afterwards. But let's keep it for now. There's an important constraint, I made it up. So the maximum debt the bank offers per person is 10 million euro. I don't know if it's realistic or not. I don't know, I never asked the bank for money, so maybe it's less, actually. I don't think they will give me like 10 million euro. Absolutely not. But there is one thing which could be more realistic, actually, and this is insurance for loans. Because I think it's not, is it for loans? No, is it if you have a deposit on your bank account, the government or the central bank is guaranteeing for 100,000 euro of your deposit. So if the bank goes bankrupt, they will pay you back like 100,000 maximum. This is a real constraint. So maybe this real constraint here should have been like 100,000 euros, because then as a European Central Bank, I would be interested. Okay, so what's your total debt? And then I know if you're doing well or not. But anyway, let's take this as a working example. So there's people, and the maximum debt per person is 10 million euro. And there's people, and I'm interested, like, what is the total debt? So why is it a numeric query? It's not counting query, of course. I'm not counting people in there. So I just want to do what I want to do is a sum, of course. Okay. Now, of course, do I have the sum here? Of course, now we know that so now you're the banker. You have a new role. No, you're the banker. Okay. If I'm gonna ask you, so what's the total debt in your bank? You don't have to do the math. Okay, so you say like, okay, this is something like, well, actually it's pretty easy. So it's 2,807,799.56. Okay, cool. And then I'm gonna ask, the three of you, okay, so Bob, Charlie, and Sander, and you tell me how to debt. So you say like, well, I don't have any debts, of course. You say like, I have like 150, fair enough. And Bob will tell you, I have like 7K, but it's okay. Yeah, so then I know, I'm sorry that you just bought a house and you owe like 3 million euro. It's a lot of money. What? It's a villa. It's a villa in Frankfurt West End. If you see, and well, it could be actually an apartment in Frankfurt West End. No, it could be a villa. For 3 million, you should get a villa. But anyway, so this is it, right? So you know that you can't really tell me, the true value. So of course. So well, how can we fix that? So let's take, well, we know the Laplace mechanism for counting queries, right? So we have an example. So let's naively try to use it. So this is a naive attempt. It might work, it might fail. So let's try. So how was the Laplace mechanism for counting queries? I'll finish in 10 minutes, okay? So the Laplace mechanism for counting queries is that, again, we take, sample with scale 1/epsilon and then report with the true. Okay, so this is our Laplace mechanism we just discovered today. Will this ensure the differential privacy bounds that we need to satisfy for all neighboring data sets and any outputs? This is a question. If I want the sum and add the Laplace noise on top of that, will it guarantee this differential privacy? And that's a good question. I mean, this is maybe it's a simple example, and I will go through an actual maybe counterproof or proof. I mean, you can prove or you can disprove by counterexample, but you need a formal proof because this is a mechanism. You say, well, yeah, I'm going to use this mechanism for protecting privacy and it will ensure differential privacy. The only way you can really tell is to make a formal proof. And formal proofs are hard and easy to do something wrong. And sometimes it looks okay, and someone else finds out like, well, there was something wrong in the proof. I'm sorry about it, and everything breaks. And I've seen these examples in NLP already, unfortunately. So that's maybe why we should go through and see whether it holds or not, just to really see, first an experience like, will it hold or break? I said naive attempt, so maybe it will break. But let's try to see how it breaks. So, but this should, I mean, if this were true, if this were different, if this mechanism would protect privacy, then this must be satisfied for any output or any neighboring data sets. Okay, so this is the guarantee. And this is why you're in the data set, and you're in the data set because I promised you epsilon of 1. Nobody will find out that you bought a house. Or maybe you did. Well, I don't know, but with some probability of not actually revealing the truth. So this is the data set again, and let's try, for example, okay, so let's take the simplest approach. So D would be all D persons, the full data set, and D prime would be I'll remove LEs. Okay, why? Well, why not? It's an arbitrary choice, but in this example, just to show how I can reveal the truth, it will break. It will break very badly. And why? Because this is the outlier. This is the outlier in the data set. And this is easy to show on outliers because everybody has to be protected equally. If I take some random, some average value or Xander, maybe I wouldn't show why it will break. So, but it has to work for any neighboring data sets and any values. Okay, so let's say the outlier. So the true will be the sum we just computed before. So 2007 and so on, like basically summing up the whole thing. And the D prime would be sum of those things, which gives me this number. Okay, so we have the true value for D and the true value for D prime. So what we're gonna do next is to plug into the PDF of Laplace. Okay, so here, what are we plugging in here? So what does it mean? 1 over 2 B. Okay, yeah, of course, because, right, I mean, 1 over epsilon B was 1 over epsilon for counting queries. Okay, for counting queries, epsilon was 1 over B. So I plug in here the PDF of Laplace, and I just plug in already the B as 1 over epsilon. Okay, everybody knows what I'm doing here. So this is the true value for the first data set. So for the 2 million something with LEs, and this is the value for the other neighboring data set. Okay, so then I just have this ratio of these probabilities, and this to hold this has to be bounded by x of epsilon, right? This is what I want to prove or disprove. Okay, so I plug in these two probabilities, and I'm gonna do, well, this will cancel out. This is awesome. This fraction, so epsilon will go up. Okay, epsilon will go up. Nice. And I'm gonna plug this up, and this will turn into plus. So some algebraic operations which everybody should be able to do with a little bit patience. And if you do it quickly, then you make mistakes and forget minus signs. So do it, do it properly. And I hope this is correct this time. So no, actually, I did just the first thing. I just get rid of these fractions, and here I'm gonna plug this up, change, and put epsilon in the front, right? So okay, I did this here, and I have these x, so epsilon, and then these two things. And now, well, so you can, what we need to do is, this is also bounded. Well, this should be bounded by 1 in order to hold, right? I mean, if we want to get this, then this thing should be bounded by 1, and it's not. It is smaller than 1 for some values, but for some values, large values, I don't know, like you can compute this per hand or ask Wolfram alpha, whatever, but not for all values will it be smaller than 1. So for some values of y, it will just exceed 1, and this won't hold. So this doesn't work. This is not differential private mechanism for real valued queries. Okay. So this naive solution with doing this Laplace with 1 over epsilon violates differential privacy. Okay. Does it make sense? What we just did here? Yeah, we tried and failed. This is great, but we show like, oh yeah, this is a counterexample how it will fail. So we choose like maybe the worst case example, because maybe if we chosen Elise, Bob, Charlie, and Xander, and then just remove Xander and Elise, Bob, Charlie, I guess we would have something which looks like a private mechanism, but it would be wrong. So we, it's hard. It's bad. Sometimes maybe it's hard to prove by example because it has to work for all neighboring data sets. Anyway, how to fix this? How should we fix that? How can we fix this thing? Yeah. Normalization. What would you normalize? So how would you would take the numbers and normalize it?
You can probably use a Z-score normalization.
So how would you do that exactly? What does it mean exactly?
You take the average of the data, and then you take the difference of the average with each of the data that is there.
You would normalize it, okay? That's interesting, and this is interesting. So can you try formally? You take this data set, take this, try what you're saying, and try to use this naive mechanism again. And I can guarantee you it will break for some or the other example. I can guarantee it will break. Because what you're saying is that you change something in your database. Maybe if you normalize it, it doesn't. Okay, so you're doing something in the database, and maybe you would fix it. Okay, so that'll be awesome. If you can try, maybe you have a solution for this. But maybe the solution is not in the database itself, but somewhere later on. So, any idea what can we do? So I don't have a solution right now. I think this is for you to take away and think about it. If you have not a counting query, but something which is where it's numbers coming out, and still we want to use the Laplace mechanism, but maybe we need to change something, and what this something will be. One hint for this is this, the maximum depth. This will influence something. This is a very important piece of information. Having said that, this is all for today. So I want you to do two things. What was that again? Some sort of proof of Laplace mechanism. The other was playing around with the scale, was it that? And maybe now you have a special, you have a special task to think about the normalization, and everybody think about how to fix that thing. And this is where we finish today, and we'll take up next time. Thanks a lot.